The session number 8 is starting. I will share it. So please take your seats.
Please.
Yeah, thank you. Thank you. So every slot is 30 minutes. So people that are presenting when it's 5 minutes away, we will just wait my hand so that everyone knows. So it's my pleasure to invite Vladislav Mantic as our first speaker. So please.
You can wear it as well. Okay. Perfect. Thank you. Good afternoon, everybody. I will talk about the singularities, stress singularities in generalized continuum contact model for interface crack in anisotropic biomaterials. This is a joint work with my previous PhD student, Maria Herrera. What are interface cracks? Interface cracks are located in the interface between two materials. We consider otherwise a perfect interface. They appear in heterogeneous solids and structures, in laminates, multi-layer, protective coatings like delaminations, coating detaching, in composites like the bonds between reinforcement and matrix, delamination in laminates, in polycrystal like intergranular fracture, and also they originate problems with electronic devices and of course adhesive bonded joints. The key feature of interface cracks between different materials, similar materials, is that they usually propagate under mixed fracture mode because they are trapped at the interface like a weak surface. So the tendency to contact between crack faces in a zone adjacent to the crack tip is much higher than in cracks in homogeneous materials. Thus, the effect of friction between crack faces is much more relevant in interface crack than in cracks in homogeneous materials. Which is the framework of this work. We are considering perfectly bonded flat interface where there is a crack, but otherwise the interface is perfectly bonded. We consider linear elastic materials like adherence. We consider Coulomb friction law in sliding with a uniform friction coefficient. And if we look on this example where we have a flat interface, here we have a crack. If this the solid is subjected to shear stress, it's typical that a long contact zone appear at one crack tip and extremely short contact zone or no contact zone actually at the other crack tip. The situation or the solution in the neighborhood of the crack tip with the long contact zone, relatively long contact zone, can be modeled by a semi-infinite interface crack in frictional contact, and this will be a problem we are going to study. Okay, so we consider infinitesimal, semi-infinite interface crack in frictional contact, and we look for the solution in this problem. Starting from Kondratiev work on general asymptotic expansion of displacement, the stress singularity, we know that it can be given in the sum of the power law term and power logarithmic terms. And we will focus on this, in this work, just on the power law terms of this asymptotic expansion, which are associated to some singularity exponent lambda. We consider generalized plane strain. It means that we consider three components of displacement, but depending on only two coordinates. There are two fundamental interface crack models. The first one introduced by Williams, which is the open interface crack model, which considers traction-free crack faces, but it leads to complex singularity exponents with real part 1/2 for non-zero Dundur's bimaterial parameter beta, which leads this complex singularity exponent leads to oscillatory crack tip solution with infinite zones overlapping and oscillating stresses. To avoid this, let's say, unpleasant feature of complex of this oscillatory crack tip solution, Comninu proposed a contact interface crack model. She considered a contact zone adjacent to the crack tip, And she obtained a square root stress singularity for frictionless contact, but real singularity exponent different from 1/2 for friction contact. To generalize this interface crack model for isotropic materials, there were a lot of effort put in this area. These are some publications on open model, but I will focus just on the contact model. And in the work by Wu and Nemad Nasser and his PhD student in 1992, they discovered that in the frictionless contact model by Komninu, depending on the elastic symmetries in the adherence, the singularity exponent can be 1/2, or it can be a complex number. So again, the oscillatory character of the solution can appear for some elastic symmetry. Much more difficult seems to be the generalization of the friction contact model to interface crack in anisotropic material. The most advanced attempt is by the Sung and Chung from 2003. So we consider generalized plane strain with 3 components of displacement depending only on 2 coordinates, x1 and x2, and the interface crack is located in x1, x3 plane, so interface crack is perpendicular to x2 axis. In the Sung and Chung work, they consider particular friction sliding conditions. They consider just friction shear stress vector, either perpendicular to the crack front or parallel to the crack front. If this assumption were correct for the problem, so they obtain a correct solution. But if this assumption were not correct, so the solution was not correct. So we propose the following Coulomb friction condition for sliding. We consider any orientation of the friction shear stress vector given by the angle omega with respect to axis x1. So we can write this Coulomb friction condition for sliding, where omega is unknown, a priori unknown angle. The objective of this work is to develop semi-analytic methodology for the calculation of the singularity exponent, lambda in generalized plane strain, for considering 3D Coulomb friction law between interface crack faces, allowing any sliding direction. And we apply Stroh formalism for the anisotropic materials, for the linear elastic anisotropic materials. Our procedure is similar to the procedure by Chen for frictional sliding of 2 semi-infinite edges. So the considered configuration is like this. We consider the crack in the plane x1, x3 located on the positive part of the axis x1 and the perfectly bonded part of the interface on the negative part of the axis x1. We consider any direction of friction stress vector. So we are looking just for power law terms of this asymptotic expansion. From Stroh formalism of anisotropic elasticity, we obtain this general expression for power law solutions in each material m equal 1 or material m equal 2 for displacement and for tractions. The lambda is the singularity exponent. Matrices A and B are complex 3x3 matrices given by the elastic properties of the material. And also complex matrices EM are diagonal matrices that depend on the singularity exponent lambda and the polar angle theta. They are basically capturing this power law variation together with this exponent r to the power of lambda or r to the power of lambda minus 1. We apply the following interface condition. In the perfectly bonded part, theta equal to plus minus p, we have continuity of traction and continuity of displacement. In frictional sliding contact in the crack, we have for theta equals 0, we have continuity of tractions, continuity of normal displacement, and friction sliding law by Coulomb. We also consider collinearity of the relative tangential displacement vector and the friction shear stress vector in the contact zone in the crack. I have skipped the brief course on Stroh formalism. If you have time and you are interested, I can show you how does it work. Now we use this. Okay. We use this interface condition I showed previously. We plug in here a general expression for displacement and traction, and we obtain this condition for once we remove the r to the power lambda or r to the power of lambda minus 1. For unknown coefficient vector q1, q1 hat, q2, and q2 hat, they are of dimension 3. And this is for the perfectly bonded part, and for the frictional sliding part, we have these conditions. Expression for this diagonal matrix for these particular angles are very simple. Here is the example. They are basically, in this case, is just identity matrix. This is the reason we selected this position of the interface crack. What we do now is to remove all except coefficient vector q1 hat, q hat, and we keep q. We move the material matrix used by who. In terms of the impedance positive infinite matrices, positive matrices, M in this the Stroh matrix. We use this star matrix. We get this formulation from these two independent equations. We can write them in this form, where k is a complex number. At the moment, is arbitrary. And if this matrix bracket is invertible, we can actually find almost the final equation. But this doesn't happen always. I forgot to mention that we consider just an integer singularity exponent, because integer singularity exponent correspond to polynomial solutions. Actually do not see the cracks, so are relatively simple. And this matrix in square in these brackets is not invertible for lambda equal to 1/2. So from this point, we consider just lambda also different from 1/2. In this case, this matrix is invertible, and we end up with this equation. We can rearrange it to this form, which is actually the scalar equation, and introducing a new characteristic matrix of the interface crack with frictional contact in this form, in terms of the bimaterial matrix, and denoting the elements of this characteristic matrix like M hat, Ij, we get the first eigenequation for singularity exponent lambda and omega, the angle of the friction shear vector. If we apply the collinearity condition, proceeding in a similar way, we get this expression. This is the collinearity condition. And from this M hat matrix, we obtain this second eigenequation for lambda and omega. Looking in this characteristic equation, we see that is periodic function of lambda. So the period is 1. So if lambda is a singularity exponent for the problem, also lambda plus any integer number is a singularity exponent, which is of course relevant for the problem solution. For the particular case, we skip if lambda is 0.5 plus n, some an integer number. This matrix is not invertible, so it can be written following some result by think in terms of this symmetric positive definite matrix L and skew symmetric matrix W. And this matrix equals for this particular value of angle to the 2 times imaginary unit times W, which is a skew symmetric matrix. Depending on the elastic symmetries in the adherence, this W matrix can have different properties. And for example, the material are similar. Dundur's parameter is beta. This matrix is 0, so 1/2 is the singularity exponent. If we have balance by material with the elastic symmetry plane coincident with the interface, so we lambda again 1/2 is like singularity exponent, but omega is p0 minus P, etc. And similarly, depending on the plane of symmetry, if the plane of elastic symmetry is perpendicular to the crack front, then we have again 1/2 like singularity exponent, and omega is p½ or minus p½, etc. In general, anisotropy, when all these components of this skew symmetry matrix are non-zero, so 1/2 is not a solution. Looking for some problem, we solved this problem using MATLAB cone, where the previous formulation was implemented. We consider a composite carbon epoxy lamina in both, like material 1 and material 2, but with different orientation of fiber. In the material 1, the angle of fiber is fixed, 60 degree, and in the material 2, we are changing the angle of fiber. So we obtain this variation of the singularity exponent. We consider just here just lambda different from 1/2, and we see that if friction coefficient is smaller, this variation of singularity exponent are smaller. If you look on the angle omega, how it depends, it is independent of friction coefficient, and this, for example, a totally new result, and it changes with the orientation of the fibers in the material 2, and for the laminate plus minus 60, these angles omega are 0, 90, minus 90, 180, etc. If we check the fulfillment of the energy, frictional energy dissipation condition, we see that only weak stress singularity with lambda larger than 1/2 fulfill this dissipation condition. But if lambda is larger than 1/2, so energy release rate is 0, J integral for the vanishing radius of the integral path is going also to 0. So we cannot use the classical fracture mechanics. And one of the possibilities to use the couple criterion of finite fracture mechanics, which considers finite crack advance. So to conclude, we have introduced a new approach to deduce asymptotic series expansion at the tip of a frictional interface crack for any linear elastic material. We deduce two nonlinear eigenequations for lambda and omega in terms of this characteristic matrix. We have seen that in the monoclinic materials with the plane of symmetry x2 equal to 0, friction coefficient doesn't have influence on the sliding angle. For certain elastic symmetries, lambda can be a singular solution, but the stresses at the crack are 0. And we can use this couple criterion for this problem if lambda is larger than 1/2. I would like just to mention this approach can be used also to characterize the solution at the transition line between stick and slip zone. And finally, that these present results were checked by our general semi-analytical code for stress singularities and multi-material corners with frictional sliding. Thank you for your attention.
Thank you very much for your thoughts. Is there any questions from the audience?
Can you please make it more clear if we consider shift of loading the crack, because you need contact between faces. So, and the question is, if in an arbitrary loading we will have this condition, or even if we consider shift, there can be openings.
Normally, is the situation, typical situation is like it was in the first plot. It is a typical situation if we have some compression, at least in isotropic material, that we have some relatively long contact zone, and by commonly there is a contact zone here, but this is totally subatomic size, so we cannot forget it. So this is the opening. This crack tip, we have fully open crack, and this creates typically bubble, and we can have contact zone depending on the configuration of the problem, which is for more than 1/2 of the crack size, or can be a few percent, 10%, 5%. It depends on the problem. We solve many problems of this, for example, for this interface crack along the situation where we have on contact zone or it's very small, which cannot be detected by the numerical method. And then if the crack is larger, so we can have a relatively large contact zone. So the contact zone, it can increase depending on the size of the interface crack, the position with respect to the load, etc.
Okay, so thanks to the speaker once more.
Thank you.
Thank you. Don't worry, microphone. Yes.
Okay, thank you very much. Okay, I would like to present a talk on the design, in fact, of approximation of dynamic of elastic body with impact. And maybe what I think are the most issues to design efficient schemes. So first I will present the framework, the very basic framework, in fact, of linear elasticity body on a rigid obstacle, and maybe the issues. Then implicit time machine schemes, the problematic of explicit time machine schemes, what can bring Nietzsche's method in that context, and finally a space-time Petrov-Galerkin approximation that we are looking at the moment. So first, when you have an elastic body, a linear elastic body, which come into contact with a rigid foundation in the dynamic, with here a finite element approximation is quite, of course, it's a very classical, thing. It's looked like that. No, okay. Yeah. And it is written here as what is called the measure differential inclusion. So of course, here is a mass matrix, a stiffness matrix. Lambda n here is a contact force or the contact pressure. And here it is, the contact condition is written in terms of inclusion. That's working very well. Okay. And of course, when it has been proven that this kind of equation has solution, but it is ill-posed in the sense that there is many solutions of this equation where there is impact. So just to illustrate this, if you use a basic time machine scheme, it's a midpoint rule. So you write a midpoint rule on that problem. It's not difficult, of course, but you obtain this kind of thing. And if you test this, here this is a numerical test on a 2D bouncing ball, a ball which is bouncing on a rigid obstacle again. So you can see on the top here the evolution of energy. On the bottom, the evolution of the contact stress at the lowest point of the ball, in fact. And here, when the time step is, in fact, greater of the CFL condition for the, in a sense, equivalent explicit scheme. So, in a sense, with a large time step, so you have something which is more or less regular and which is more or less here dissipated in a sense. So no, but you have some spurious oscillations here which appear, which is difficult to see if it's normal or not, because okay, this ball there is a dispersion of shock waves inside, but okay. And when the time state is decreasing, the thing get worse and worse. And in fact, here with the smaller time step, the things become to be unstable, and there is on the contact pressure here is not we cannot do anything with this. Okay. So it's it's very specific of contact problem, dynamic contact problems, that you decrease the time step and it becomes more unstable and more unstable. Okay, to illustrate this, to understand this fact, we just look at the one-dot system. You can view as a contact node, simplified contact node, just a mass with a spring on the rigid obstacle. The corresponding equation here, the simple system. And it's not difficult to see that here are the solutions of this problem, and what is unknown is it is, of course, a very, very well-known thing. What is unknown is the velocity after impact. When the mass impact, the equations which are here do not prescribe any velocity after impact. So any velocity after impact make a solution of this problem. Okay, this is well known in rigid body mechanics. It's very classical, and usually you have to prescribe an impact law. For instance, an elastic impact law with restitution coefficient E, which is between 0 and 1. If you want an elastic restitution, you prescribe E equal to 1 or equal to 0 for no restitution. Okay, if it's not clear, the sense of this restitution coefficient for deformable bodies. And in fact, what can be shown here for you, what could be noted is that when you take E equal to 1 in finite element discretizations, okay, you will have energy conservation because you have conservation of the velocity after impact. This is good. But the contact nodes cannot land to the rigid obstacle. It's not possible because if they land, you lose the kinetic energy. So okay, they are infinitely bouncing, very rapidly bouncing. This is not and when you choose E equal to 0, okay, the contact node can land because they lose all the velocity at impact. So they land correctly in a sense for deformable body point of view, but of course you dissipate energy. You dissipate energy only with the contact, which is not physical in a sense. So there is a dilemma, and okay, the previous equation, which was our equation here has many solutions, but in a sense, none are satisfactory completely. So some existing strategy for implicit time machine schemes, maybe one of the first important work in that context is the one of Moreau and NSCD schemes. At the origin, this was a theta method applied to the problem, and they take account of the restitution coefficient inside the scheme, in a sense, in a certain implicit way. But of course, for deformable body, generally, it is assumed that E equal to 0 because otherwise you have generally some instabilities. And of course, you are energy dissipative in that sense. There's a lot of work which has been done on that framework, of course. And what we proposed quite a long time ago now, it's mass redistribution. What is mass redistribution is simply, okay, one of the problems is inertia of the contact nodes. So, okay, just suppress it, or just redistribute the mass in the mass matrix, in a way that contact nodes have no mass. And of course, it's a bit it's a bit variant, but it can be done, for instance, with different discretization between displacement and velocity. So in a more natural way than just put 0 on the mass matrix. And if you do that, you obtain a well-posed semi-discretized in space finite problem. So it's no longer measure differential inclusion, but it's a standard equation, ODE equation. It is energy conserving, and most of the time machine schemes becomes convergent with that trick. And this is, for instance, here the same numerical test as previously, and here the same time step, and you see that there is no more large oscillations of the contact stress, and it converges when the time stress goes to 0 to an energy conserving solution. We avoid this kind of so mass redistribution can be a part, at least, of the solution to have a good scheme in that context. And there's further work in, for instance, for plate problem and so on. And okay, this was for implicit scheme. The mass redistribution works only in a sense for implicit schemes. Why? Because you suppress the mass on the contact boundary. So on the contact boundary, you have a sort of quasi-static evolution. And so you solve something on the whole contact boundary. You cannot have an explicit scheme with this. And the question is, can you have explicit schemes for dynamic with impact? And of course, you have. This is a classical thing. First, maybe with penalty method. With penalty method, you can use standard explicit schemes, such as a central scheme. It works. And one scheme which here with a Lagrange multiplier method, and the classical scheme is Pauli-Schatzman 1. It is based on Verlet scheme, so the central difference scheme. And so this is an explicit part with the contact condition, which is prescribed here. In fact, in a semi-implicit way, it depends on the coefficient of restitution E, which is also included in this scheme. If you take, for instance, E to 0, you are fully implicit, in fact, in contact stress. So, okay, so this is explicit, but the contact force is implicit. So if you have multi-body contact, generally, you cannot be fully explicit, because you have to solve your contact multiplier here you cannot solve it locally, generally, it depends. So it may be the drawback of that. And a very classical scheme also, it was a Taylor-Flanagan scheme. It was very popular in the 90s. It is also based on Verlet schemes, but the leapfrog form of Verlet scheme. But in fact, the scheme is equivalent to the central difference scheme. And the trick is on the half time step. The velocity is prescribed to 0 if there is the contact to enforce what is called the persistency condition. And this leads to stability, but this leads also to of course, to dissipation. 5 minutes. Okay, I have to speed up a bit. Okay, so Nietzsche's method in that context, it's quite. Okay, I will not present the details. It had already been presented. This is Nietzsche's method in the dynamic context here, with the term here, which describes the contact. And what is, okay, properties of Nietzsche's method, we skip. And this is a benchmark is on a 1D problem. 1D problem is specifically, in a sense, a severe test because there is a traveling wave which is not, with no attenuation. And this is a bar which is compressed at t equal to 0, and which have a periodic solution, which is easy to compute. And here, if we make some tests with all the methods I introduced here, you can see that here, all the methods, in fact, at the left here, it's a convergence in displacement. At the right here is a convergence on contact stress. And of course, you have a rate of convergence which is log to 1/2, but this is due to the regularity of the solution. And for instance, all the methods converge at the same rate because of the methods which are reasonable methods in a sense, including the penalty. The penalty is in red here, but with the penalty, it can be seen with if you choose, you have to choose very finely the coefficient of the penalty coefficient, because if you choose this large, you have a good approximation of displacement, but bad approximation of the contact stress. And this conversely, if you have a too low coefficient of penalty, you have a good approximation, a better approximation of contact stress, but bad approximation of displacement. Okay, just I will skip this, and maybe this is the current work with Victor Kovtunenko and Adrien Petrov. We try here to a space-time formulation, Petrov-Galerkin space-time formulation. This is this formulation, but why it is called a Petrov-Galerkin? Because the space for test function is not exactly the same that the space for here for the primal variable. And okay, and it's possible here to derive some finite element approximation of this. And for the moment, we are in a 1D problem, and it's not so bad, but not very better than the method I told you before. And what we try at the moment is to choose the right approximation to recover, in a sense, the good property, for example, of the mass redistribution, and to improve the results. So, okay, so thank you. So, as you understand, I think it's not so easy to have a good approximation, both having no spurious oscillations and good property of energy conservation in that context. Okay, thank you very much for your attention.
Questions from the audience? I have one. I mean, in case the barrier is like elastic or viscoelastic, there is no more rigid.
Yes.
Are those problems still there, or you?
Yes, the problem are exactly the same because you have still some shock waves, and you can test all on this kind of simple problem because, in fact, for instance, in 2D, you have a sort of dispersion of shock waves, so it is less severe test than the 1D problem, for instance. No is not. Thank you.
Is there any question? Okay, so let us thank the speaker.
Thank you.
So the next speaker will be Giacomo Petraglia.
Thanks. So thank you for the introduction, and good afternoon, everyone. I'm Giacomo Petraglia. I'm a PhD student from Politecnico di Torino, and I'm here to talk about the last project in which I'm involved too. And I started working on this during my mobility period that I spent in the School of Mathematics and Statistics at the University of Glasgow, hosted by Dr. Ariel Ramirez Torres, and supervised by my home university supervisors that are Alberto Sapore and Pietro Cornetti from the Department of Structural Engineering and Alfio Grillo from the Department of Mathematical Sciences. So I just want to warn you about this work, that it's very work in progress right now, because we just started to work on, so during my mobility period, so it's just a few months work, and it's also a little bit off topic with the topics covered during this conference. But we think that in the moment in which we will have, the moment we will have a robust and reliable numerical implementation of this model, the model will be applied to some contact mechanics problem, and because our research group we have a peculiar way to interpret and to study continuum mechanics, because we believe that non-standard experimental framework requires some specific kind of continuum mechanics modellistic approach. And which are these particular experimental benchmarks? In this case are biological media, in particular tumor growth. And we have that multicellular aggregate works very well as an in vitro proxy for early stage tumor growth. And it is well known in the literature also that in this particular experimental benchmark coexist very different kind of external activities, such as biochemical cues and also mechanical solicitation. And it is also well known that such particular mechanical loads, for example, compression loads, can trigger internal structural transformations, and this favor progression of the growth of the biological media despite the presence of pro-growth chemical signaling. So that could be also very useful to treat and to avoid the growth of tumoral tissues. And so our challenge is to build a modellistic framework in order to study the mechanical response of these multicellular aggregates, and to couple this mechanical response to plastic-like remodeling processes and damage that in this kind of situation could happen very, very often. So this is an eyesight summary of our framework, and I want to underline that we will work with. We are assuming that our continuum is monophasic, so we are only considering the solid part of the biological media, and then we work in finite deformation regime. We will start from kinematic framework, because we will decompose with a multiplicative decomposition the tensor gradient of deformation f into three different tensors that could be associated to every of the considered physical processes that are coupled in our modelistic framework, that are viscoelastic, plastic, and damage distortions. The viscoelastic and plastic distortion will be computed as unknowns of the problem, and they will be forced to be isochoric processes through proper constraints. Whereas the third of these tensor from the multiplicative decomposition, the damage mapping, that will be expression of the distortion related to the damage process, will have an expression that will be prescribed a priori, and it will be furnished in the next slides, and will be isotropic and coupled to a phase field variable that will represent the unknown related to the damage process. The phase field is one of the most versatile and well-known technique to deal with damage processes in continuum media, and it's basically this scalar variable that can span between 0 and 1 that describes punctually in our domain the damage state of our material. When phi is equals to 0, we have that material, it's completely pristine, so we don't have damage at all. And when phi is equal to 1, we have that material, it's fully damaged. So after the calculation of the force balance laws through the principle of virtual power, then we have to do some necessary constitutive assignments. And we will integrate a grade 1 phase field model, such that happens in the vast majority of the literature about phase field model in fracture mechanics, and we will treat the viscoelastic response of the continuum through time fractional operators. So we will start to get deeper in this dissertation by working on the multiplicative decomposition that we did in the spirit of the works by Michunovic. And we, as I anticipated before, we decomposed the tensor F in these three tensors, and every process can be associated to one of these tensors. The first one is F gamma, and it is related to the plastic distortions, and we are forcing this process to be isochoric. And that means mathematically that the determinant of F gamma will be equal to 1. The same happens for the tensor Fe that is associated with the viscoelastic distortions, and also this process is forced to be isochoric. So the determinant of Fe is equal to 1. A different treatment as the damage mapping, so the tensor related to the distortion from the damage, that will have a prescribed expression that will be in the next slides. So this kind of assumption yield the final equation in the slides, and that is J equal to JD. And this means that the determinant of the tensor of the gradient deformation will be equal to the determinant of the damage mapping. So that means that the only volumetric process that is going on in our framework is the one related to the damage process. So in order to work with these constraints in the framework of the principle of virtual power, we express our constraints in their differential form. So we simply applied the Jacobi's formula to express the time derivative of f gamma and f in the first and the last equation of the slides. And then we have also the prescription from the damage mapping, that is from the work by Schutte and Bruns. And we have that this is the final expression of Ft that is dependent by the phase field through this function f. So evaluating the time derivative of the determinant of ft with this prescribed expression, we will yield the second summand of the last equation. And so we have that the constraint J equals to JD in its differential form will be this one. So now we need a tool to insert and to use these constraints inside the principle of virtual power. And so we need to define the Chetaev condition. But to do so, we need to define firstly the spaces, the functional spaces in which the admissible velocity for our problem live. And so we have these three spaces, and we have to assume that the constraints are ideal. So that means that the reactive forces that are generated by our internal constraints expend zero virtual power. So if we translate mathematically this constraint, we have the Chetaev conditions related to our two constraints. And we evaluated them by simply calculating the functional derivative of our constraints with respect of their arguments, and then evaluated along the direction related to the admissible velocities. And so, and then we imposed this expression equal to zero because we want that these are ideal constraints. At this point, we have all the ingredients to follow the approach outlined by Bonnet and Wood that express their constraint form of the principle of virtual power, in which the contribute of the internal power is split into two different contributions. The first one is related to the active internal power, and the second one is related to the purely reactive power that is also null for the hypothesis that we introduced before. So now we are able to define the three functionals, and to define the active internal power, we introduce the set of the generalized virtual velocity of our interest in the model, and we can note that for the phase field we are considering the rate of the phase field and the rate of its gradient. So we are in a grade 1 theory for damage, but it is not the same for the remodeling, because we are only considering the rate of the gradient of the remodeling tensor, and we are not considering its gradient. So by doing this kind of observation, we can define this functional, and we can see that we have the active part of the first Piola-Kirchhoff tensor that is dual to the gradient of the admissible generalized velocities. And we have also a generalized stress related to the remodeling process. We have a generalized force related to the dual to the rate of phase field, to the admissible rates of phase field, and we have a generalized stress dual to the gradient of the admissible rates of the phase field. Now we define also the null reactive power, and to do so we need, of course, the Chetaev conditions that we defined in the previous slides, but we need also two Lagrange multipliers, one for each of the constraints that we are considering. We need also their variations, and we need the mathematical expression of the constraint. So by localizing the principle of virtual power through standard techniques, we can express the force balance in its strong form. So we have the equilibrium equations from the first three equations. Then we have the two constraints that, of course, has to be valid in all our domain. And then we have our natural boundary conditions. After that, we notice that we have more unknowns than equations. So we need to do some constitutive assignment. And we follow the theory adopted by Gurtin that has its roots, of course, in Coleman and Knoll approach. In fact, we are using the second principle of thermodynamics through in the form of the Clausius-Duhem inequality as a constraint. And this is the weak form of this inequality. And we can simply evaluate the strong form of the same inequality. So at this point, we have to define properly this free energy, this CR, in order to deal with all the physical processes that we mentioned before, and in order to couple and to create some constitutive assignment for all the generalized stresses and forces in their active part, of course. And to implement the viscoelastic nature of the continuum media, we followed the theory outlined by Ehringen that claimed that our free energy is dependent by U, that is this set of variables of our problem that has in common the fact that they are dependent from that variables at the time t, so they don't have any memory of what happened before t, is an instantaneous measure of this variable. But CR is also dependent by the history of the Cauchy-Green tensor that has this expression. So we can define CR as the sum of two contributes. The first one that is dependent by the set U, so it's an instantaneous, is the instantaneous and, if we may say, the elastic part of the Helmholtz free energy. And then we have a second summand that is direct expression of the viscoelastic nature of the media, modulated by this function that is a degradation function dependent by the phase field, and this function can be designed such that for phi equals to 1, so when we have a fully damaged state, this G is equal to 0, and when phi is equal to 0, so we have pristine material, this function is equal to 1. So we don't have any change with respect to the undamaged state, to an undamaged material state. So we have arrived at this point. So the next step of our work will be to refine and finish the definition of our constitutive assignments, in particular of the constitutive tensor inside the viscoelastic integral, and by defining some dependency with respect to the deformation history CT, and why not also by a phase field history function. Then we will develop a finite element solver within the Phoenix environment to produce some numerical results. Then we will validate it against some aggregate compression data to quantify the model predictive capabilities. So thank you for your attention.
Thank you very much. Is there any question from the audience?
May I ask a question? Consider a simple situation, spherical multiscale aggregate
Yes.
under compression and negative tension.
Mm-hmm.
How damage field will evolve? Will it sense sign of pressure?
So I think that will depend. I will show you. It will depend by the characterization of this function, because for now we are trying to characterize this function such that it cannot be below. It cannot be negative. So a negative f function means that the biological media will incur like or a growth damage-driven, a damage-driven growth, or a self-healing process. So for now that we are considering only damaging processes, so without self-healing processes, we expect that we pull off the compression state, the phase field will be like irreversible. So it won't change with respect to what happened before the decompression.
I have a curiosity. Also, in this scheme, do you think you can also include some friction at the interface when you have contact?
Yes, without any problem, because I think that our way to treat this, the continuum mechanics in general, permits us to add this kind of physical phenomenon and processes very easily. So I think that it could be other than possible, also useful for the final project.
Thank you. Is there any other question from the audience? Otherwise, let us thank again our speaker.
Thank you.